Okay, so this is section 4.4, and we're going to be talking about the mean value theorem. We don't actually start with the mean value theorem, though. All right, we're going to start with Rolle's theorem. Before we get into Rolle's theorem, let me give you a little bit of history of Rolle's theorem. So Rolle's theorem is named after Michel Rolle, who was a French mathematician, and he was a contemporary of both Newton and Leibniz, right? So remember back when we started calculus, we said, okay, these are the two guys that kind of invented calculus. So Rolle was at the same time as they were, and he did not buy it at all. He did not think that this system of doing mathematics was useful and that provided good results. He thought it was flawed, and was kind of, vocal about that. So it's ironic that we have named a theorem after him that is one of the cornerstones for calculus. And this is not the work that I think that he would have wanted to be famous for. He did a lot of work in other areas, but it's the one that's got his name attached. This theorem was actually proved over 400 years earlier by a mathematician in India, but it's named Rolle's theorem because of a Eurocentric view of mathematics. I don't know, history. Okay, so that's a little bit about Rolle. So let's go ahead and look at this theorem and see what it's saying to us. We have this function, and we have some properties for this function. We're going to want to start with a nice function. So f is continuous on some closed interval. It's differentiable on the inside of that interval. And f of a equals f of b. So when I, when I think about what we're doing here, if I draw a quick example, I want a function that's going to be continuous, so no breaks, no jumps. Differentiable, so no sharp corners, no vertical asymptotes. And it's going to start and end at the same y value, right? So maybe it goes up and then down. Maybe it just goes up, maybe it just goes down, okay? All right, so that's the function that we're working with. And then here's our conclusion. There exists at least one number c inside that interval where f prime of c is 0. So let's look at the maybe a few different possible things that could happen. The function could bend up, turn around, and come down. Since it turns around, we know that, we're going to get a horizontal asymptote. And we'll talk about that in detail in a minute when we prove it. Or it can go down, but again, it's going to have a turnaround point. It could do both. It could do lots of things in between. We could have more than one possible value of c in between where the derivative is 0. This is just saying that there is at least one. And it's not telling us what that value is. Okay, so it's a little bit weak in that sense, but we saw that also with the intermediate value theorem, where it gave us the existence of a number, but it didn't tell us how to find it. Okay, so same thing here. All right, so I want to look at an example. Here's a function f of x equals x squared minus 3x, and we have an interval 0 to 3. First of all, when we're working with a theorem, it's important that we are careful with checking the conditions of the theorem, right? And here I've labeled them 1, 2, 3. We have to check these 3 conditions. If these 3 aren't met, then it doesn't make sense to talk about, a conclusion for the theorem, because we don't know if the theorem is actually saying anything here, right? So like, suppose I say to you, if you do your homework, then I will pay you $1 million, okay? And then you don't do your homework, well, then it doesn't make sense to talk about whether or not I'm going to, send you a check for $1 million because you didn't do your homework anyway, right? So we need to check the conditions of the theorem before we can even think about the conclusion, right? So all right, the conditions or the hypotheses. Okay, so first we need to note that f is continuous on the interval 0 to 3. And in this case, my function f is a polynomial. When we talked about continuity, we said all polynomials are continuous everywhere. So f is continuous on 0, 3 because it is a polynomial. Okay. Next, f is differentiable on the open interval 0 to 3. And again, polynomials are really great. They're also differentiable everywhere. All right, and then finally, the last condition is that f of a equals f of b. So what we're going to do is we're going to say, okay, I have this interval 0 to 3. Let's actually compute what the y value is at each of those points. So f of a is f of 0, which is 0 squared minus 3 times 0, which is 0. F of b is f of 3, which is 3 squared minus 3 times 3, or 9 minus 9, which is also 0. So f of a equals f of b. Okay, now that we have the three conditions for the theorem, that means that it gives us a conclusion. So therefore, there is a number c in the interval 0 to 3 with f prime of c equals 0. Okay, so that's checking the conditions and then stating the conclusion of the theorem. Now, in this case, because we have this polynomial, we have formula for f, we can actually go through the process of finding that number c. Okay, so now let's find the c, or maybe more than one. Okay, so what I'm going to do, since this says f prime of c is 0, let's first find what f prime of x is. A polynomial, right? So we can use the power rule. 2 comes down, so derivative of x squared is 2x, and then minus 3. So f prime of c is 2c minus 3, which is equal to 0. So then we solve. So I get 2c equals 3, c equals 3 halves. That is indeed in the interval. That's our value for c. Okay. All right, now this example doesn't feel like it did a whole lot. We're basically just saying, here's a theorem, how do I use the theorem, and that's it. We're not going to go into great detail with the applications for Rolle's theorem, because the main application for Rolle's theorem is to help us prove the mean value theorem. The mean value theorem is a better theorem. And I'll explain what that means to a mathematician when we look at the mean value theorem. But maybe first, let's go ahead and see if we can give a proof of Rolle's theorem. So here's what I'm going to do to prove Rolle's theorem. We know that in order to talk about Rolle's theorem, we need this f of a equals f of b. When we give a proof of a theorem, we're going to assume that we have all of the conditions for the theorem, and then show that we get the conclusion. Okay, so when we have a proof, we assume the three conditions. Okay, that means that we have a function f that is continuous and differentiable, and f of a equals f of b. What we're doing here is saying, let's just call this f of a equal f of b. We know they're the same. Let's just label that as k. And what we're going to do is we're going to break this up into three cases. Let's suppose that the function is constant. F of x is always equal to k for all the x's between a and b. Okay. Well, if that is the case, then f prime of x is 0 for all x's in a, b. If the goal was to show that there is just one value of c where the derivative is 0, we just showed that any number in between a and b works. So any number in a, b works for that value of c. All right, now If that's not the case, if we don't have a function that's always constant, then that means that the function is either going to be bigger than k or smaller than k at least once. And it could be more than once. But what we're doing is we're saying, okay, if it's bigger than k, it looks like this first case. Smaller than k, it looks like the second. It could be something where it's both, but again, if it's both, then it's bigger than k for at least one value. So that would fall under that case too. Okay. All right, so here's what we're going to do. Let's suppose that f of x is bigger than k for at least one of these values. Note that f is continuous on AB. Okay, so we have a function that's continuous on a closed interval. And what we're going to do is apply the extreme value theorem that we had from 3.3. Okay, the extreme value theorem said that if you have a continuous function on a closed interval, it has both an absolute minimum and an absolute maximum. So we apply the extreme value theorem. So f has an absolute max on AB. Okay. All right, so an absolute maximum exists. And I know that wherever that absolute maximum is, I'm just going to label that as my number C for now. Because f of x is bigger than k for at least one value, I know that this is not going to be equal to our k, right? So we're just going to make a quick note. F of c is bigger than our k, which is the f of a and f of b endpoints. Okay. All right, now what we're going to do is we're going to say, well, I also know that this function is differentiable. Okay, so since f is differentiable, on AB, f prime of c exists. Right? That's what differentiable means. It means the derivative exists. Okay, and since it's differentiable at all the points between a and b, then the derivative exists on all those points. All right, since I have an absolute max on my interval, so since f of c is an absolute max, and is not an endpoint, then c comma f of c is also a local max. So f prime of c equals 0, or f prime of c is undefined. And again, from 4.3, we said because of Fermat's little theorem. Okay, except that we just said that f prime of c exists, so we know it's not undefined. So f prime of c equals 0. And again, that's what we wanted to show. There's at least some number where the derivative is 0. Okay. The third case is suppose f of x is less than k. This is exactly the same as case 2, except with a minimum. Okay, and we don't need to rewrite all of that out. That's enough, and we have a proof now. All right. Let's see what Rolle's theorem really gets us. It's really about helping us show the mean value theorem. Or another way to say that is we can improve on Rolle's theorem with something called the mean value theorem. All right, so here's the mean value theorem. It starts off the same way. I have a function that's well behaved, right? It's continuous on a closed interval AB and differentiable on an open interval AB. But we don't have a third condition. And that's what makes this a better theorem. It's more flexible. Okay. Then there exists at least one number c in AB where f prime of c equals this crazy quotient. One of the things that I want to note here is what exactly this f of b minus f of a over b minus a is. So let's suppose that I have some graph, right? And we have some function y equals f of x. So here's a comma f of a, here's b comma f of b. And if I connect them with a line, then the slope of that line so the slope of this line is the change in y, so f of b minus f of a, over the change in x over b minus a. And that's exactly what this is. So when we see this quotient, this is really just the slope of the line connecting our endpoints. Okay. What would happen if f of a equals f of b? So if f of a equals f of b, then the slope would equal 0 because I would have 0 over some number. And so what this would say is if f of a equals f of b, then I would have an f prime of c equals 0, which is exactly Rolle's theorem. So the reason that we call this a better theorem is because Rolle's theorem is like a special case of this. In the situation where f of a equals f of b, this gives you the same conclusion. But if you have a function where f of a is not equal to f of b, this also gives us some information and Rolle's theorem doesn't. So that's why it's an improvement on Rolle's theorem. All right. Again, let's go through an example verifying the hypotheses and just seeing what this gives us. Right. So here I have a function f of x is the square root of x on the interval 0 to 9. And I have to verify the hypotheses. I only have 2 in this case, though. So we need to show that f is continuous on the closed interval 0 to 9. Okay. And this one is not a polynomial, so I can't get away with just saying, oh, it just is. But we did talk about, in our section on continuity, that the other functions that we typically work with are going to be continuous on their domains. So root functions and trig functions and exponentials and logs are all continuous on their domains. So in this case, f is a root function. So it is continuous on its domain, which is 0 to infinity. Okay, so then it's definitely continuous on 0 to 9. Right. Next, we need to show that f is differentiable on the open interval 0 to 9. And the open interval is important here because if I look at a graph of this function, at 0, I have a vertical tangent line. So the derivative, looks like it would go to infinity. But it actually gets worse than that. If I have a point and I don't have some points on the graph on both sides, I can't approach from both sides with secant lines, right? And that's how we defined a tangent line and thus a derivative. We have to be able to approach from both sides. So this is kind of like doubly bad, right? If I could approach from one side, I would get an undefined value for my slope and hence for the derivative. And secondly, even if that didn't happen, I can't approach from the left, so that's no good. So at 0, we're right out, but we don't need to show that it's differentiable at 0. We're going to show it's differentiable on the open interval 0 to 9. I don't want to get hung up on showing details for things like that. So I think if we look at a continuous function and we just say, okay, on 0 to 9, there's no vertical tangents and no sharp corners, that's good enough. So continuous with no sharp corners, no vertical tangents, and that's going to be enough for differentiability for our purposes. Okay. When you move on in math, and maybe you're majoring in math or something like that, and you get to some analysis classes, then you can be a little bit more picky about this. But I think for our class, we're going to say this gives us a good enough idea. All right, so that's the hypotheses of the mean value theorem. So now we write the conclusion. So therefore, there is a number C in the open interval 0 to 9 with f prime of C equals f of B minus f of A over B minus A. And since I know what A and B are, I can actually fill this in. So A is 0 and B is 9, so this is going to be root 9 minus the square root of 0 over 9 minus 0. So this is just the number 1/3. So that's my conclusion. Now, let's actually see if we can find that value C. Okay. So my function f of x is root x. Before I differentiate it, I'm going to rewrite it as a fractional exponent. And that just makes it easier to take the derivative that way. Don't make a silly mistake. So I can just do the power rule. Half comes down, lower the power by 1. Now that I'm done differentiating, I'm going to get rid of this fractional exponent. So the half power is like a root, and the negative means it goes in the denominator. This is 1 over 2 root x. Okay, so f prime of C is 1 over 2 root C, and I know that's equal to 1/3. Okay, so just taking the reciprocal of both sides, 2 root C is equal to 3. Root C is equal to 3/2. And then we're going to square both sides. When you square root both sides, you'd get the plus minus deal. That doesn't happen when we square both sides. Okay, so we just get C equals 9/4. And that is indeed between 0 and 9. And that's the only C value that does that. And so we're done. All right. Let's see if we can prove the mean value theorem. In order to prove the mean value theorem, we have to kind of get things set up just right. So what I'm going to do, remember when we looked back at the mean value theorem, we said, okay, this is the slope of the line that connects my two endpoints. What I'm going to do to start with is I'm going to write the equation of the line that connects these two endpoints. Okay, but I don't have a formula for f. So this is going to be a little bit abstract here. Okay, so we start by finding the equation of the line. That connects A comma f of A and B comma f of B. Okay, so we already know that the slope of that line is f of B minus f of A over B minus A, and I'll just pick the A comma f of A as my point, and we're just going to call this line L of x. So I'm going to use the same notation for linearization. Maybe L of x is not great, but it's not really a linearization that we're doing here, but I'll just use L for line. Okay. Maybe I should back up just to be clear. I'm going to use the point slope formula for the line. Y minus y1 equals m times x minus x1. Okay. So y minus f of a equals this crazy slope times x minus a. And then I'm just going to add f of a to both sides. Okay, so we get y equals f of a plus this fraction f of b minus f of a over b minus a times x minus a. And this is the equation of our line. Okay, so I can label this as like L for line. It has nothing to do with linearization or anything. It's just the equation of my line. Okay, what I want to do to prove the mean value theorem is to use Rolle's theorem. The problem is that for Rolle's theorem, if we go back, we need these two endpoints to be the same, right? F of b has to be equal to f of a. And for our example, that's not the case, right? So how do I make use of Rolle's theorem? What we're going to do is we're going to find something in between that works for us. Okay, we're going to find a different function that we can apply Rolle's theorem to that sort of connects back to my function f. And what I want to do is show you a picture of that first. Okay, so here's my function f, y equals f of x. That's my blue function here. And what I'm going to do is I'm going to define a function g of x to be the distance in between our line that we just found the equation of and our function. It's just going to be the two subtracted. Okay, so what we're going to do is we're going to say let g of x equal f of x minus L of x. Okay, so it's f of x minus f of a plus f of b minus f of a over b minus a times x minus a. Okay, well, why are we doing that? The reason that we're doing that is because at a, the two things are the same, so g is 0. And at b, the two things are the same, so g is 0. And those two match. So I can apply Rolle's theorem to g of x. Okay. Right. So L of x is a line. So it is continuous on AB and differentiable on the open interval AB. Okay. Remember when we're proving or we're writing a proof for a theorem, what we do is we assume the hypotheses of the theorem and try to show the conclusion. So we're assuming that f is continuous and differentiable. Okay. So assume f is continuous on the the closed interval AB and differentiable on the open interval AB. Okay, and since g is just the difference of continuous functions, it's continuous, and it's the difference of differentiable functions, so it's differentiable. Okay, so it's the difference of continuous functions, so it's continuous on the closed interval AB, since g is the difference of differentiable functions. It is differentiable on the open interval AB. G meets all of the criterion for Rolle's theorem. Okay. So we apply Rolle's theorem to g of x. Okay, so let's see what that does for us. That means that there's going to be a value for c somewhere in between where g prime is equal to 0. In order to see what that means, let's go ahead and look at what g prime of x is equal to. So g of x is f of x minus f of a minus f of b minus f of a over b minus a times x minus a. So if I take the derivative of g, right, so I take a derivative on the left, I get g prime. If I take a derivative on the right, the derivative of f of x is f prime of x. F of a is a constant, so that's 0. F of b minus f of a over b minus a, that's the slope, so that's just a constant multiple. That's going to hang out. And when I differentiate x minus a, the derivative of x is 1. The derivative of a constant on its own is 0. Okay, so g prime of x is equal to f prime of x minus this fraction that represents our slope times 1. So that's just it. Okay, so g prime of c is equal to f prime of c minus f of b minus f of a over b minus a. And because of Rolle's theorem, we know that this is equal to 0. So all we have to do is add that slope to both sides. And we get that there is a number c where f prime of c is equal to f of b minus f of a over b minus a. That's exactly the conclusion of the mean value theorem. There exists a number c where that happens, and that's what we have here. Okay. So the theorem is proved. Okay. We already went through an application of the mean value theorem, but really one of the things that the mean value theorem does is open up different possibilities if we look at it in the right way. So what we're going to do next is we're going to look at something that are called corollaries to the mean value theorem. And a corollary is kind of like a new theorem, but it's not very different. So what it is it's just looking at this same theorem in a certain context that will hopefully illuminate something, right? So here's our first corollary. A function with a derivative of 0. So let f be differentiable over some interval I. If f prime of x is equal to 0 for all x's in that interval, then f of x is a constant in that interval. Okay. And well, why is that? Okay. So if f is differentiable over an interval, differentiable means it's also continuous. Okay. So we can apply the mean value theorem, just abbreviate it MVT. So by the mean value theorem, there is a c with f prime of c equals f of b minus f of a over b minus a. Okay. Except that we're told that the derivative is 0. So f prime of c has to be equal to 0. So if this fraction is 0, then the numerator is 0. So f of b minus f of a equals 0. So f of b equals f of a. So I didn't show that the function is always constant. I just showed that the two endpoints are the same. Okay, but what we can do is we can pick any 2 points in the interval and apply the mean value theorem to it. So I'm not going to call them points. We'll say this applies to any 2 numbers A and B in the interval. That means that any 2 numbers in the interval that you pick give you the exact same output. And that's what it means for a function to be constant. It means all the values are the same. Well, if you pick any values, any 2 numbers you pick in the interval, they're always the same, right? So f of x is constant. Okay, so what this does for us is it says, yeah, if you take the derivative of a function that and you get 0, then your function was constant. Now the other way we already knew, if your function is constant and you take a derivative, then it's 0. We knew that. What this is saying is those are the only functions that give you 0. Okay, if you take the derivative and you get 0, you had to have started with a constant function. All right. Corollary 2, constant difference. So if f and g are differentiable on an interval I, and their derivatives are equal, then the 2 functions don't have to be identical, but they have to be only a shift from one another. F of x has to equal f of g of x plus some constant. Okay. And once again, what this theorem is not saying is something that we could already show, right? If f of x was equal to g of x plus c, then I know that their derivatives would be equal, because if I differentiate both sides, on the left I get f prime, and on the right I get g prime plus 0. Okay, but this is going the other way. It's saying, well, I'm not starting off by saying that the 2 functions are off by a constant. What we're doing is we're starting off by saying that the derivatives are equal, and is there a way for that to happen? Okay. And the answer is no, right? If the derivatives are the same, then the functions are just going to be a shift from one another. So first, let me show you a quick proof of that. Let's let h of x equal the difference, f of x minus g of x. Okay. So then if I take the derivative on the left, and then on the right, I'll have f prime of x minus g prime of x. Okay. And since we're assuming that f prime is equal to g prime, then this is 0. Okay. So now I have a function h whose derivative is 0. So by corollary 1, h of x equals a constant c. So then we just substitute back. So f of x minus g of x equals c. So f of x is g of x plus c. Okay, here's a way to sort of visualize this theorem, or this corollary rather. Let's suppose that I have a graph of a function f of x. And we have another function g of x that has the same derivative. That means that at every point, the slope of the tangent line is the same. Or another way to think about that is that the function points in the same direction. So if I have a function that's always moving in the same direction as f, it's going to be a copy of that function, except that it didn't need to start at the same spot. It could have started somewhere else. But otherwise, it's going to have the same shape, right? So if it has the same shape, but it could have just started in a different spot, then it's just always going to be off by that constant. Okay. Let's look at a third corollary. That says corollary 1. I should say corollary 3. Function with a derivative of 0. So let f be continuous over the closed interval a, b, and differentiable over the open interval a, b. If f prime of x is positive, then f is increasing, and if f prime of x is negative, then f is decreasing. And this is something that I think that we've probably already discovered, right, through looking at graphs and derivatives, and I think that we've probably talked about this. But here's a way to show it maybe a little bit explicitly, right? Instead of looking at a graph, right, because I already know, or we have already sort of made use of right, suppose I have some function, okay, here the tangent line is horizontal, so here where the function is moving up, right, I know that f prime is positive, okay, here I have a horizontal tangent, so in between the derivative is negative, and then over here the derivative is positive again, okay. What we're doing is we're going the other way and we're saying, all right, if the derivative is positive, that always means the function is increasing. If the derivative is negative, then it's decreasing. And we can do that without looking at a graph, right? So it's a way to kind of maybe firm up what we've already been assuming. Okay. So let's just suppose that we have a function that's continuous and differentiable on, on these appropriate intervals, and also that f prime of x is positive. Okay. So what we want to show is that f is increasing, right? Well, let's go ahead and apply the mean value theorem. So there exists a C in AB with f prime of C equals f of B minus f of A over B minus A. And since f prime of x is always positive for x's in AB, I know that this is a positive value. Okay. AB is an interval, so B is bigger than A. So B minus A is positive. So what I can do is multiply by B minus A. So I get that f of B minus f of A is positive, or f of B is greater than f of A. That's what it means to be increasing, right? That your later x value has a bigger function value than the earlier one. Okay. Okay. So f is increasing. All right. And the second one is the exact same, just, an inequality switch, right? It's d. If it's negative, then we'll get decreasing. Everything just flips upside down. Okay. So the mean value theorem is not something that I think that we whip out to solve a bunch of quick problems. It's really more about establishing what's going on with derivatives, and it provides kind of a logical basis for us. So we'll have some homework in this section, but really what the mean value theorem does for us is it kind of provides a way for us to really understand what the derivative is. And it's, we're going to use it, in the next couple sections to show other things, like how parts of graphs relate to each other. And we'll use it in chapter 5 to help prove the fundamental theorem of calculus. Okay, but it's kind of like a theoretical basis for what we're doing. It's not like a direct problem solving type of thing. Okay, so we'll solve a few problems with it. There are some goods problems that you can solve, But that's not what it's really important for. What it's really important for is it sort of tells us how derivatives work in a sense. All right, I think that's it for this section.